All right, everyone, good afternoon and welcome to the second press conference of the 245th meeting of the American Astronomical Society. It is Monday afternoon, January 13th at 2:15 p.m. Eastern. We're here in National Harbor and we're here for the press conference Supernovae and Massive Stars. So before we get started, just a reminder to please silence your cell phones and anything else that makes noise. And just a note that we are recording this on YouTube. And we will be archiving it there. So the press kit is going to be updated with the videos and the slides and the press releases from today. It's already got some of those things from this morning's session. I will finish uploading the rest as soon as we get done with this press conference. And that will be updated by the end of the day. You can find that in the press section of our website for the meeting. And it's also linked from the press conference's Slack channel. And we are here today with a fantastic lineup of speakers. So just for anyone who hasn't attended one of these press conferences before, a reminder of what this is going to look like. I'm going to give a very brief introduction here, and I'm going to introduce all of our speakers and their presentations. And then we're going to move right into their presentations back to back. They're all going to give their talks. And we ask that you please hold your questions until the very end of all of this. And after that, we're going to move into a Q&A session for the whole panel. And we will take questions both in the room. We've got a handheld mic that we will bring around to you. And we'll take questions from online. My name is Susanna Kohler. I'm the press officer for the AAS. I am joined here by Carrie Hensley, the deputy press officer. And we may also press into service former President Feinberg again. I'm sorry, Rick, I should have asked you in advance to assist us by running the mic later. We are a little short-staffed today. So for this session, as I said, we are looking at supernovae and massive stars. And unsurprisingly, this is featuring a lot of fantastic results from JWST and Hubble. So I'm really excited to see this. Our lineup today, we're starting with David Coulter from the Space Telescope Science Institute, who's going to be speaking on JWST discovery of a distant supernova linked to a massive progenitor in the early universe. Next up, we're going to have Melissa Shahbandeh from Space Telescope Science Institute, speaking on the core collapse supernovae as key dust producers, new insights from JWST. Then Emma Lieb from University of Denver will speak on JWST tracking the expanding dusty fingerprints of a massive binary. Kristina Monsch from the Center of Astrophysics, Harvard and Smithsonian, will talk about stellar pyrotechnics on display in a superstar cluster. And Emily Leiner from Illinois Institute of Technology will discuss a blue lurker emerging from a triple system merger. So with that, I'm going to go ahead and set this up for our first speaker. And I'm going to this time close this in advance. Okay.
Well, thank you very much for having me. I'd love to kick this thing off for you guys. My name's Dave. I'm a postdoc at Space Telescope Science Institute, and I'm thrilled to share with you this discovery of one of the most distant supernovae of JWST. So I'd like to kick this off. Let's see. There we go. Why should you care about supernovae? I claim that supernovae are connected to a huge diversity of astrophysical phenomena, from galaxy evolution to gravitational wave progenitor, as well as heavy element production and its distribution. And that is what I'm going to focus on in this talk for this story. So we'll start at the beginning. This is the universe writ large, and I want to draw your attention to the beginning of the Big Bang, the middle, and the present day. Now, in the beginning, there really was mostly just hydrogen and helium. And this chemical mix formed the first stars, and these stars were considerably different than the stars today. They were massive, they were hot, and they had truly gargantuan explosions. And so what happens is the hydrogen burns into helium, and as the stars evolve, they produce all the other elements that we see on the periodic table. So the carbon, oxygen, nitrogen, so on and so forth. And then the explosions of these massive stars distribute this material to the surrounding environment, which are then reuptaken into successive generations of stars. And that's how we get planets and eventually life. So there's this narrative arrow here where we go from no heavy elements at the beginning of the universe to heavy elements in today's world. Okay, so we've been doing this. We've been looking at supernovae. We've been studying their nucleosynthesis, or how they create the elements. And we do this from the ground, and we see thousands and thousands of supernovae. And soon, with the Rubin Observatory, we'll see tens of thousands. And this pushes out to a little bit a redshift less than 1, so it's pretty local. And we've done better with HST. Over the last couple of decades, a few dozen have been found. And these have been found out to like redshift 2. And to put that into perspective, redshift 2, the light, when it left that supernova, is roughly around the time that our solar system started forming. So this is far back in time from our perspective, from our sun's perspective, but it's still not quite in that very early exotic time when the elements were truly different and the milieus were truly different. And so that's where JWST comes in. We don't know how much JWST will find, but we can start to push to the beginning of these first stars and hope to see their explosions. And so there was this fantastic survey called JADES. And this survey was an extragalactic survey studying galaxies, studying the earliest galaxies, how they assembled, how they formed, and characterizing them with multicolor images. Okay, so the important thing about this survey is they went back to the same field and they took picture after picture. And for transient hunters like us, we could subtract those pictures from each other. And what remains is something that's changing. What remains is usually a supernova. And so you can see in this field, it's about 25 square arc minutes. But if you hold your pinky out at arm's length, it's about a fraction of a pinky nail. So all of these supernovae, these 80 supernovae, are happening in that very small area. Pretty much anywhere you look, if you look deeply enough, you'll find a supernova. So this was done very deeply, and we see about 80 transients here in these little regions that you can see. Now, JADES found a lot of supernovae, including this supernova here at a host redshift of 0.6, 0.7. So this is pretty local, really. And I bring it up there to contrast what we're doing at high redshift. So if you look at this supernova, this is the supernova that we're presenting today. This is a truly distant supernova. This was discovered at redshift 3.6 and really digging in the dirt to find this, find these objects in the noise. So if we zoom in on this, we can see the before in 2022, the after in 2023, and then the difference. And this supernova was given the name AT 2023 ADS-V. So this supernova is so far away and therefore so far back in time that when the light was coming to us from the supernova, the universe was less than 2 billion years old. So that means that this light had been traveling 6 billion years before the sun ever formed. So this supernova also happened in an environment that seems considerably different than the environment that our home star lives in. There was about 1/3 of the elements, the heavy elements, in that ancient environment than there are today. And we also think that this sun, or this star, was 20 times the mass of the sun. So also a truly gargantuan explosion. So if I put this back in the context here, you can see this red vertical hatch where we think this supernova happened. And JWST is leading the way to get to earlier and earlier times in the universe to find these truly massive stars and their explosions. So I want to leave you with these takeaways, that we have seen some of these distant supernovae, and there are more to come. And this is a major step towards finding some of those first explosions. Thank you.
Hi, everyone. My name is Melissa Shahbandeh. I'm an SCCI fellow, and today I'm going to tell you about why supernovae are key dust producers. So why do we care about dust? Dust is behind everything pretty much in the universe. Dust is the building block of the universe. Dust is behind planet formation, star formation, as you can see in this image, a lot of clumps of dust can create stellar nurseries, create a lot of stars. Dust grains can coagulate and they can aggregate and create stars, and stars eventually can create things like solar system, and then we can have planets. And if we have planets, maybe eventually we can have life. And you all probably have heard that we are all stardust. So dust is important, and originally, astronomers thought that asymptotic giant branch stars were the main dust producers of the early universe. However, when JWST came along, we got these really beautiful images, and this image that you see here is showing you one of the earliest galaxies in the universe. And as you can see on the right, it's only a few million years old at a redshift of 14. And what we see here is that there is a little bit of a reddish area in this galaxy that shows these early galaxies in the early universe hosted a lot of dust. And AGB stars, as they were believed to be main producers of dust, were not old enough at the time to produce a significant amount of dust because they take millions and millions of years to shed their outer layers and produce dust. So what is the alternative scenario? It's supernovae. Supernovae are the explosion of the most massive and youngest stars, and they are therefore great candidates to produce these massive dust reservoirs in the early universe because they can explode quickly when they're young, and they can quickly spread a lot of material throughout this space and create dust grains, and eventually a lot of dust that can end up being a planet, a star. So let's say we have a lot of data or not of supernovae. What are we going to do with this? Among all types of supernovae, there were some Spitzer information that we got about 20 years ago of these supernovae that were observed with the ground-based telescope pretty well. And out of all these supernovae, we found that interacting supernovae, or type 2N, were the ones that stayed brightest decades beyond explosion. That is not what we expect from a supernova. We expect a supernova to go faint and disappear months after explosion. So seeing these group of supernovae that stayed bright even decades after explosion was an indicator that maybe they host a lot of dust in the IR. And that's why they are bright in the Spitzer. So what we did is that we went after one of these supernovae, these type 2N, that was observed pretty well and it stayed bright years and years beyond explosion. This supernova is called 2005 IP. And the reason we try to observe this supernova is to understand if these supernovae are actually the main dust producers in the early universe. So here what I'm showing you is the two spectra of this 2005 IP. So on the top left, you can see the Spitzer spectrum that was obtained 3 years post-explosion. And the bottom spectrum is the JWST spectrum that was obtained about 18 years, 15 years post-Spitzer. And as you can see, it is still bright. This spectrum is about a year ago. It's still bright, almost 20 years, 2 decades post-explosion. And what we did is that we tried to model both spectra and understand how much dust is this supernova hosting. So the Spitzer spectrum on the top, what we learned is that it is hosting hot carbon dust. But then when we looked at the JWST spectrum, almost 2 decades later, it is still bright. And then what we learned is that right now, this supernova is hosting a lot of cold silicate dust. And what this is telling us is that this supernova not only was hosting a lot of dust 3 years post-explosion, but it kept forming dust, and therefore can tell us that maybe these supernovae are somehow special, and then they can create a lot of dust over time. And you can see that I'm showing you the cold silicate dust emissions, that a signature of this about 0.1 solar mass of dust in the supernova, and then the hard carbon dust is what our results shows from the Spitzer spectrum. So then, okay, so let's say the supernova hosts a lot of dust, and these supernovae are special. Why are these supernovae special? Because as we call them interacting supernovae, these supernovae interact with their circumstellar material, and they create this cold dense shell that a lot of material starts to cool down in this cold dense shell. It condenses, and over time as it cools down, dust starts to grow. And what is the most significant thing about this shell is that it is protected from the reverse shock of the supernova, which is what usually destroys the dust that is formed in supernovae. And a lot of dust that we found in the supernova 2005 IP, we believe that majority of that dust is actually located in that area that we call cold dense shell. And these supernovae type 2N or interacting supernovae are great candidates because of this cold dense shell that protects the dust that they form from the reverse shock. So this dust can start to grow and potentially contribute to the significant amount of dust that we observe in the early universe. Now going back to the life cycle of dust. So if I start from the left, we have a star, supernova, star explodes, and then it gets older, it spreads material throughout the space, and then it creates stellar nurseries, creates stars, and the stars grow, and then they create things like solar system, and then we have planets, and then maybe eventually we have life, and then that star, for example, something like sun, a star in a solar system explodes, and then the life cycle of dust continues. So the main takeaway that I want you to remember from this talk is that from these JWST observation of this supernova 2005 IP, which was a great example of these interacting supernovae, we learned that there are massive reservoirs of newly formed dust in these interacting supernovae, and possibly that could indicate that supernovae are rapid dust factories that could be the main contributors to the significant amount of dust observed in the early universe. Thank you so much.
Hi, everyone. My name is Emma. I am a PhD candidate at the University of Denver and a NASA Finest recipient this year. I'm going to be talking to you about some JWST images that we have that track the expanding dusty fingerprint of a massive binary. So which massive binary? We looked at WR140. WR140, it's a textbook example of a Wolf-Rayet binary. Wolf-Rayet stars are massive evolved stars, no longer on the main sequence. They're characterized by having very strong stellar winds. The companion to the Wolf-Rayet star in WR140 is also a massive star. It's an O star. These massive stars orbit each other roughly every 8 years, and they're in a very eccentric orbit, meaning not very circular. So they kind of swing far away from each other and then come in close to each other at a passage called periastron. When those stars get really close to each other, the stellar winds collide, and you actually get carbon-rich dust formation. Like I said, WR140 is kind of a textbook example of a dust producer. When these stars get close to each other, that dust gets produced in kind of like a belch, and then it gets propelled outward into a dusty spiral-like nebula. So here are two images. On the left here, we can see this is our cycle 1 image. This was taken in July of 2022. On the right is our cycle 2 image. This was taken about a year later in September of 2023. So we took both our observations in 3 different wavelengths so we can create these RGB or false color images. However, I think kind of looking at them side by side is a little difficult to tell that anything has moved. If instead we overlay our cycle 2 image on our cycle 1 image in 2 different colors, we can see that here we have cycle 1 in orange, cycle 2 in blue. We can see really clearly that these shells have moved outward. A key highlight of this image is that because our background stars are white, the orange has perfectly mixed with the blue and created white background stars. It's very obvious we've lined up our images right on top of each other, and so these shells have definitely moved outward. One more way that I can show you this is with a video. So if I blink between our 2 images, here it's a little more difficult to see because we've got those bright JWST diffraction spikes that we tried to process out. But if I zoom in, we can see really obviously that these shells are moving outward with respect to those background stars. So yeah, I've zoomed in here on an area or a feature that we call the C1 feature. This is where most of the shells in our images you can see outward to. So how did I go about measuring the speed of these shells? So what I did was take what we're calling a flux profile or array. So I take a line, I start at the position of the stars in the center of our image, and I take that line all the way through all the shells, and I can measure the brightness along that line. And so each peak of that brightness profile corresponds to one of our shells. So here I'm showing all three of the regions that I studied for the second image. But if I zoom in on just that C1 feature, our dashed line here is a cycle 1 profile, and the solid line is the cycle 2 profile. And we can see really clearly that these peaks are not right on top of each other. The shell has definitely moved. If I divide that distance that it has moved by the exact amount of time that separates our images, we can get a velocity for these shells to be roughly 2,700 kilometers per second. That is almost 1% the speed of light. So these shells are moving at a real clip. This number actually is really consistent with the literature for how fast the stellar wind of the WC star in WR140 is moving. So that's a consistent number, and it's definitely really moving. One secondary result that we have about WR140 from this image is not just that the dust shells are real, they're definitely astrophysical, they're not the result of any kind of imaging artifact, but also we were able to show that the shells exhibit a non-uniform substructure that persists from one cycle to the next. So we get what we're calling kind of a clumpy dust morphology within each shell. And the fact that these clumps are also visible in cycle 2 when we saw them in cycle 1 proves that they are real. And they may hint at the underlying physics, the underlying physical mechanism for how dust structure is able to, how dust formation is able to occur in a system like WR140. So my major takeaways that I want you to take are WR140's dust is expanding away at almost 1% the speed of light. It is really moving. The second is that these irregularities in the dusty morphology around WR140 is really hinting at the underlying physical mechanisms, and it may, the dust formation process in a system like WR140 may be inherently irregular or non-uniform. And lastly, WR140, but also other WR binaries that also create dust should be enriching their local environment with this stardust. And that stardust is the same dust that goes into later star and possibly planet formation. So if you want to talk to me more about this, I have a poster this evening at 5:30, poster 163.1. Email me anytime. And we also had a paper come out today, just about an hour ago, which you can come and talk to me about anytime. Thank you.
Hey, good. Yeah, thank you everyone for being here. I'm happy to continue our press conference with the exciting discovery of a cosmic fireworks display in the young superstar cluster Westerlund 1. So the James Webb Space Telescope observations that I'll be presenting today are the result of an international collaboration of over 50 researchers who are part of the EWOX project, which is a combined X-ray and infrared survey of the two superstar clusters, Westerlund 1 and Westerlund 2. So what are superstar clusters? A superstar cluster, or an SSC, is a very massive young open stellar cluster that is generally defined to have a mass of more than 10 to the 4 solar masses. They contain thousands of members and typically host a large amount of massive stars that will ionize their surroundings. And if we look at the mass distribution of open clusters in the Milky Way, we can see that superstar clusters are actually really rare. So, but despite being rare in our galaxy today, they used to be very common in the early universe when the formation of stars was much more prevalent. So the main questions we try to answer when studying superstar clusters are: how do massive stars lose mass throughout their evolution? How do massive stars shape their surroundings? Oops. And what can superstar clusters teach us about the formation of stars and planets in extreme environments? Westerlund 1 is the perfect target to help us answer those questions. So first of all, it's one of the most massive, if not the most massive superstar cluster known in the Milky Way. Then it's also relatively nearby, and it hosts a large or a diverse population of massive stars across a wide range of evolutionary phases. And most importantly, Westerlund 1 is also young enough to potentially host stars that still have protoplanetary disks. So being one of the closest and most massive superstar clusters in the Milky Way, Westerlund 1 is the ideal target to study the formation of stars and planets in active starburst environments. Okay, so this archival image here of Westerlund 1 was captured in 2013 by the VLT Survey Telescope, or VST, which is located in Chile. So visible light observations like this offer insights into the broader structure of the stellar cluster, as well as the stellar content. However, they do not allow us to study the stars in the center of the cluster, or like in the core, and how massive stars in this cluster shape their environments. And this is why we need to observe superstar clusters in near-infrared, or in infrared wavelengths, excuse me. So JWST's near-infrared camera, or NIRCam, can pierce through the thick dust in the cluster core, revealing a previously hidden population of stars, as well as the cluster's structure that was previously hidden at optical wavelengths. But if we want to truly understand the role of dust, so the role that dust and the gas play in the superstar cluster and the effects of stellar wind on their surroundings, we need to look even deeper. And this is where JWST's mid-infrared instrument, or MIRI, comes into play. Okay. Sorry. I was shocked for a second. It's not showing in the mid-infrared. MIRI allows us to map at incredible detail and resolution for the first time the warm dust and gas that surrounds the massive stars in Westerlund 1. So our MIRI image reveals the intricate structure of the stellar cluster and the interstellar dust that is produced by stellar winds. And the MIRI image that is shown here shows all kinds of different structures. So we see, for example, extended nebular emission, droplet-like features, dusty shells, and outflows surrounding the massive stars in Westerlund 1. So unfortunately, I don't have time to go through all of them in detail, so I will only highlight a few special discoveries in this data set. So for example, MIRI revealed outflowing bipolar loops around the red supergiant W75, which have not been observed before. So red supergiants are at the end of their evolutionary, or at the final stages of their evolution, meaning they're basically about to die. And studying the different structures of the outflows around such evolved stars can give us important clues on how these stars die. So in contrast, W20, or the nebulosity around W20, which is actually an even larger red supergiant than W75, it shows a completely different morphology, namely a cometary-shaped outflow, which is pointing away from the cluster center. And here we think that the morphology of this outflow was probably shaped by the cluster wind of Westerlund 1. And last but not least, our MIRI observations also revealed the stellar wind in the form of shell-like outflows from W237, which is one of the largest known stars in the galaxy. And just so that you get a feeling of how incredibly big the star is, so if you place it at the center of the solar system, it would encompass, so it would reach all the way to Jupiter's orbit. So W237 shows a well-defined bow shock, which is facing the cluster core, and its rather circular shape indicates that it has been less affected by the cluster wind of Westerlund 1, which might indicate that this star might be located near the center of the cluster. Okay, so all in all, these JWST observations have not only revealed an incredible fireworks display in Westerlund 1, but they've also uncovered previously unseen nebulosities and ejecta around the most massive stars. So these observations have an incredible legacy value, and they will allow us to study the formation, the evolution, and the death of the most massive stars, as well as their feedback onto the surrounding environment. And I'm sure there's a lot more exciting discoveries to come from this extensive data set. And thank you very much.
All right. Hello, everybody. I am Emily Leiner, and I am an assistant professor at Illinois Institute of Technology in Chicago. And I'm talking today about a blue lurker that emerges from a triple system merger. So first things first, the question on everybody's mind, I'm sure, what is a blue lurker star? So the story really starts with this star cluster, M67. And this is a collection of several thousand stars that were all born at the same age. It turns out that when stars are born, they're rotating really rapidly. And as they age, they spin down and rotate more slowly. So M67 is a 4 billion year old cluster. A typical star in the cluster is rotating around once every 25 days or so. That's comparable to our own sun. And my team looked at this cluster and found that there were actually like a scattering of strange stars that were rotating a lot faster than that. They were whipping around once every few days. So we called those stars blue lurkers, and they're stars that looked really totally normal. Like looking at an image like this, you could not pick one out and say, yeah, that star looks really weird. But they are spinning suspiciously fast for their age. So we set out to figure out why these stars were rotating so quickly. To do that, we pointed the Hubble Space Telescope at a blue lurker star in M67. And we found that the blue lurker was not a standalone star. It was actually in a binary system. And that binary companion was, in fact, a white dwarf, so the burned out core of a dead star. And white dwarfs are actually really tiny. They're about the size of the Earth. So they are really hard to find, especially when they are sitting directly next to a sun-like star like the blue lurker we observed. So I'm showing you an image here of the star Sirius. It's a bright star in the night sky, and it actually does have a white dwarf companion. If you look closely, it's sitting right there, just to give you an idea of how hard it is to detect these things. Hubble is actually the only instrument that is capable of doing it. So you've heard a lot about JWST today. JWST could not have found this star. Hubble is still very important. So we found a white dwarf sitting there. And that actually was not that unexpected for our team. There was a bigger surprise, which is that we were able to measure the mass of the star with Hubble. And we found that the white dwarf was far more massive than it should have been, or that we were expecting. So massive, in fact, that it could not have formed from any normal star in this cluster, M67. So what on earth was happening? It turns out the story is really complicated, and thankfully the people at the Hubble press office have prepared a lot of art to walk you all through what happened to make this bizarre system that's this rapidly rotating blue lurker with this surprisingly massive white dwarf. So we actually think that the system started as a triple system that contained 3 stars, not unlike our own sun. 2 of them were in an inner binary that was very close together. These 2 stars are orbiting each other every few days, probably. And then there was a 3rd star much further out, orbiting around that inner binary, with a period of a few thousand days. About 500 million years ago, the 2 stars in that inner binary merged. And they would have formed a massive star about 3 times as massive as our sun. And that's much, much more massive than a typical star in M67. That merged star continued evolving, eventually swelling up into a giant star. And as it grew, it began expelling material, some of which fell onto that outer companion, which is what is illustrated here. Once the envelope of that giant star totally blows away, which it will eventually, only the hot core of that merger remains. And that is the white dwarf that we detected with Hubble. And the white dwarf is much more massive than normal because it descended from that merger, which was much more massive than a typical star in the cluster. As the outer star fed off of all of that material that was lost by its companion, it grew a little bit bigger and bluer and brighter, but it also started rotating faster because accreting all of that material spun it back up. Now, remember, a blue lurker looks pretty much like a normal sun-like star if you just look at it in an image like this. But if you were able to zoom in, you would see that, in fact, there is like all sorts of star spots and prominences, the star would be flaring. And that's because it's rotating really fast. Fast rotation generates a strong magnetic field. And the magnetic field leads to all of these things like spots and flares and things like that. So this was our only clue that this entire complicated evolution had happened and that there was ever another star sitting there. Now, currently, the blue Lurker star is sitting there in a binary with a white dwarf. The blue Lurker is going to also continue to evolve in the future. It's going to expand into a red giant star. It's going to burn out and leave a white dwarf just sitting there. So eventually the system is going to probably evolve into a system of 2 white dwarfs in a binary. It's a little unclear exactly what's going to happen. Maybe it'll sit there like that for a long time. It's also possible those 2 white dwarfs will spiral in and merge together. And when that happens, they will probably detonate a type 1A supernova or some other type of explosive event. So the conclusions, we set out to answer a relatively simple question: why are blue Lurkers rotating so fast? It turns out it's because they have gobbled up material from a companion. But in the process, I think we actually opened up a can of worms and stumbled on something that's quite a bit more far-reaching and profound, which is that this star formed in a triple system. Now, triple systems are actually fairly common. About 10% of sun-like stars are actually in triples. But we have, by and large, just been totally ignoring triples in models and simulations. And we are just starting to understand how these types of systems evolve. And in this one example of triple evolution, we can see how many different types of interesting astrophysical products are connected, from a triple of just 3 normal stars to a massive merger, to an accreting star that might show up as an X-ray binary, to double white dwarfs, to even things like type 1A supernovae. And this is forming from triple evolution, which we are mostly not even considering. So I hope the story of the blue Lurker can inspire you guys to remember that triple stars are out there. They're fairly common, and they are producing a lot of very interesting astrophysical objects that we want to understand. Thank you.
Very nice. Thank you so much. So we're going to go ahead and move into our Q&A session. So for those of you who are in the room, we've got a handheld mic that Rick is going to bring around. So you just put up your hand and we'll bring a mic to you. And if you could please identify yourself and your affiliation and who your question is for, that would be great. For those of you online, you can type your questions into the Q&A box. And again, there, please identify yourself, affiliation, who your question is for, and we will get to those as well. Yes.
I'm Martin Radcliffe with Evans and Sutherland Planetariums for David. Could you remind me what instrument on JWST did the JADES imaging, and did you have any kind of broadband photometric data that tells you something about the spectrum of that and what type of supernova it was? I'm guessing at 20 solar mass, it's probably a type 2, right? But do you have anything?
Yeah, that's right. So hopefully you can hear this okay. Yeah, we use DeerCam for that. And we also did get a spectrum of it as well. And so that's how we understood the host properties, was taking the spectrum. And you're right, we did use like the broadband photometry and fits to models to figure out that this was likely a type 2 and not a type 1 or not a stripped envelope supernova.
Hello, Connor Larison from Rutgers University. I had a question for Melissa. Sorry that I'm kind of I'll move. To motivate why type 2 supernovae are large dust producers in the universe, you showed that Z of 14 galaxy. I was wondering if you had a sense of like what % of these really high redshift galaxies that we've discovered seem to have large amounts of dust content. Is it almost all of them, or was that more like a unique situation?
Well, I'm not sure, but these are the one that I showed is one of the two of one of the most recent papers that showed that these two galaxies at redshift 14 are hosting a lot of dust, and whatever that is contributing to that amount of dust should be less than 5 million years old, and then type 2 supernovae or core club supernovae are a great candidate for that.
Great, thank you so much.
That hand up back there? There we go. You first, was you?
Eddie Barron, Planetary Science Institute. My question is for Emily. Just could you say the mass of that white dwarf?
Yes, it's 0.72 solar masses. And for some context, the expected mass for a white dwarf in M67 would be about 0.5 solar masses.
Thanks.
Yosef Zinetti, Johns Hopkins University. Following the question, what is the rate for the triple system and how fast they rotated compared to the angular velocity, omega?
Sorry, I didn't quite catch the question. You're asking about the rotation of the star?
First, the rate of this triple system supposed to be
The rotation,
rates.
the rate of the trip,
Yeah.
the occurrence rate of triple systems. So it depends on exactly what you mean. For stars like our sun, it's about 10% are in triple systems. That goes up higher as you get to more massive stars. So it's certainly not the majority, but it's not a tiny fraction either.
And the rotation velocity?
The rotation velocity of the blue lurker?
Yes.
So this one has a rotation period of about 4 days. And that rotation velocity is about 8 kilometers per second.
Hi, I'm Sungwei from Wayne State. So I also have a question for Emily for the blue lurker. So were you able to measure the chemical abundance for the white dwarf, like carbon oxygen rate or something?
So we did not do like detailed abundance measurements of the white dwarf, but it is a carbon oxygen white dwarf. We believe. So we were fitting like spectroscopic models, but not doing like detailed work.
Okay.
Hi, my name is Piramon Gundamani from University of California, Santa Cruz. I have a question for Professor Emily. So do you think blue lurker in a triple system is the main progenitor mechanism of type 1a supernovae?
I don't think that we can say that it's the main progenitor. I don't even think that we can claim for sure that this particular system is going to create a type 1a supernovae down the road. But I think what is interesting about it is a potential channel to create something like a type 1a at very late times. You know, this is happening in a cluster that's 4 billion years old. This evolution is going to happen in another 4 billion years. And it also, you know, just kind of throws a wrench in the whole, common narrative that these type 1a supernovae are all exploding 1.4 solar mass white dwarfs. I mean, we now know that that's probably not the case. And here's yet another kind of strange way that you could get them and get them at later times than you might expect.
Thank you.
If you want.
Hi, I'm Ariella from Harvard. I also had a question for you, Emily. You mentioned that there were other blue lurkers in that cluster, so I was curious if you had plans to study those blue lurkers as well, and if you suspected that they were formed from like a similar mechanism.
Yeah, it's a great question. We would love to study more, but it's hard to get Hubble to give us time to study them. So please give us more. The reason we picked this particular blue lurker is that the white dwarf was the hottest and the brightest. So it was going to take the least time to potentially find. Others of the blue lurkers may also have these white dwarf companions, but they're not as hot, so they'll be harder to observe. But I think your question, do we think other blue lurkers are forming in similar ways? We haven't proved it with Hubble, but I think, yeah, a lot of these stars are forming from mass transfer or mergers. Are they all forming in triple systems? I don't know. We would really need more Hubble time to say.
Do we have any questions online?
This question is from Bill Waller at the Galactic Inquirer for Melissa, who I can't see, sorry. The question is, how would the relative contribution of dust by type 2N supernovae compared to asymptotic giant branch stars vary over cosmic time?
So we don't have as many supernovae to make sort of like a results to say what percentage and how different they are, but we are trying to get more supernovae. And we have a strip envelope supernovae right now. We have type 2N, we have type 2P, and we're trying to compare them and characterize dust in these supernovae, and hopefully eventually in a couple of years compare to other types of dust producers such as AGB stars.
Great, thank you. I have a question, Carrie Hensley from the AAS. This one's for Emma. So that image of WR140 has an amazing amount of detail. And so I was curious if there are any other similar systems with high resolution enough data to perform a similar analysis.
Sorry. I was told to move it.
Yes,
Yeah.
that was good.
Yes, absolutely there are. We actually this year, one of our co-authors got some more JWST imaging of a few other dust producing WR binaries. That includes WR137, WR48A, and a smattering of others. Right now, if I'm not mistaken, those other systems only have one set of JWST imaging, so we kind of have to get those all processed and analyzed and out. But hopefully down the line, we will be able to add JWST, like those high resolution images of the others to kind of do a very similar analysis.
Christine Pulliam Space Telescope. I had a really quick question for Melissa, and sorry if I missed it, but what's the distance of Supernova 2005 IP?
So it's 35 megaparsecs. And I think I put in 120 million light years.
Thank you.
I see Rick's preparing.
No. Actually, I have to commend the audience because a lot of the questions that I wrote down have already been asked, and it would take me too long to find the ones that I haven't. So I'm going to pass for this one.
Okay.
You have a question? Yeah. Okay.
Hi, I'm Jessie Schweitz from the University of Wisconsin-Madison, and this question's for Emma. You talked about non-uniformity in those shells that you were seeing, and I'm curious if you have any indication if those are from rotational properties of the system or some other intrinsic properties of the system.
So it's those non-uniformities are not due to the orbital properties, but they probably are related to the dust formation process, like inherently. Like when the dust forms, it forms when the wind collision region during the periastron passage, the the wind from both the stars, that collision goes from being very smooth to being very irregular, very non-smooth. And so when the dust grains are formed right away, they actually get formed over the course of like multiple months, like around the periastron passage. And so these clumps, while they form very early on in the shell's formation after the dust grains are formed from that wind collision region.
Hi, this is Carrie Hensley again from the JWST. This question's for Kristina, and I admit this is a pretty open-ended one, so I apologize. But in terms of those 3 stars you showed at the end of your presentation and these different structures that you saw there, where are you headed next with this research? Is there anything in particular about those structures, especially that bilobed structure, that you're going to look into more?
Yeah, great question. Thank you. So since some of these structures haven't been observed before, it's like right now a riddle. We're trying to figure out what these are. But yeah, this is extremely useful, especially if you want to compare, for example, to simulations of massive stars, which will help us to understand what these structures could be. So right now it's still like we're trying to figure out what they could be. Another long-term goal we have is actually trying to find out if we find stars with planets or stars with protoplanetary disks in the cluster, and see how the presence of these massive stars affects and maybe inhibits the formation of planetary systems.
Great, thank you so much.
Okay, I'll quickly ask one. This is for David Coulter. At first you talked about how this was a very high redshift supernova, and I think you said that it was one of the highest redshift supernovae that JWST has yet found, but is it the highest redshift, or what is the highest redshift?
Yes, that's a good question. There's a lot of thought behind how to phrase these distance claims. You get different thoughts. There was a 2012 paper by Jeff Cookie that had a superluminous supernova candidate at 3.9. There are other less confidently classified supernovae in the JADE sample that could be higher redshift as well, like redshift 4, 5. I don't have the number offhand, but these have a less confident classification, and so it's hard to make that kind of claim. But yeah, we're digging deep.
All right. Any further questions? If not, let's go ahead and give all of our speakers another round of applause. Thank you so much to all of them. Thank you to their PIOs for the releases that have been prepped. All of them have releases that will be going up into the press kit today. And thank you to all of you for being here. We look forward to seeing you back again. Our next press conference will be tomorrow morning at 10:15 a.m. And it will be titled Black Holes and New Outcomes from the Sloan Digital Sky Survey. Thank you.